Today, we're very pleased to have Dr. Snigdha Panigrahi, who is an assistant professor at the University of Michigan. So she has a wide-ranging interest directed towards understanding big, diverse, and complex data. Before joining the University of Michigan in 2018, she completed her doctoral thesis at Stanford University with Jonathan Taylor. In her work, she explores the potential of new methodology at the intersection of machine learning, probabilistic modeling, statistical inference, and genomics, with a special emphasis on reconciling inferential coherence and adaptive modeling of data. She has delivered a tutorial on the recent advances in this field of research at the Simons Institute, and her research has been supported by 2 NSF awards. We're very pleased to have you here, Snigdha. We look forward to your talk.
Thank you. Thank you, Ajay, for the very kind introduction. And I'm very happy to visit this department. And this is actually my first ever trip to Seattle. So I hope to come back here more often. It seems like a beautiful city with great weather to offer, at least in comparison to Michigan. And I think I can give my honest opinion on that. All right. So for today's talk, I'm going to talk about some ongoing work with a first-year PhD student of mine, Eileen, and 2 of my collaborators at KU Leuven, Belgium, Sarah and Claire Kleskins. This is ongoing work. We hope to have the paper very soon and probably in a month from now. So it's not too far away. So this is not bluff. This is real work, which is going to drop soon. All right. So a new workflow for inference after data exploration, also called selective inference, is an actively researched topic. Selective inference provides you principled tools to infer about selected parameters that have been determined after having looked at data. Selective inference after variable selection is one such problem. It's common to report p-values or confidence intervals for variables that you selected, say, via some selection algorithm, example, the lasso. And in fact, much ink has already been spilled on Gaussian linear regression with the lasso, which is a special set of problems here. One successful approach for selective inference is to condition on the selected set of variables, or also known as the selection event here. And in particular, again, for the special class of problems, which is Gaussian linear regression with the lasso, I've listed few references, but there are many other papers which introduce different approaches with different strengths to deal with this problem. Now, at a high level, what does conditioning do for us? So, or what does the conditional approach do? Well, like I said, as the name suggests, inference is now based on conditional distributions. And what are these conditional distributions? You obtain these conditional distributions after you truncate the distribution of your data to the set of realizations that would have led you to observe the same set of selected variables as you just saw on your specific data set. So you just look at a truncated distribution or a conditional distribution. You truncate your data to the set of those realizations, which would all lead you to the same set of selected variables. That's what conditional approach does at a high level. Now, this is one way of overcoming selection bias, of course. But there is another, an alternate approach to selective inference, and I feel I should mention it, given that I am mentioning about the conditional approach, which is the simultaneous approach to inference. So it guarantees you inference for which is simultaneous over any possible selected model. So it holds regardless of the method of selection. So it's not tied to the lasso. So it seems like a very nice general approach. But again, this generality doesn't come for free. There is a cost to it, and the cost to it is power. So if I didn't tell you ever how I selected my set of variables, you can give me inference, but perhaps that inference isn't as powerful if you knew what your data underwent and you could specifically correct for the selection bias arising from that particular selection process. And another point to mention here is that the simultaneous approach has not been that computationally appealing as the conditional approach. Not that it can't be, I don't know, but for a long time, it could not scale up beyond a certain dimension. So there is, again, a computational problem there on computing those constants that allow you to widen your interval so that you have simultaneous inference over all possible selected models. Okay, so with that, I would like to mention that variable selection is not the only place where selective inference happens. There are many other interesting problems in selective inference which have been explored very recently. And I've again listed some of them, the one which does selective inference for neural network image segmentation, or selective inference for hierarchical clustering, which I think is a paper by Daniela and her group here. So there are other contexts beyond variable selection where selective inference, and particularly the conditional approach, has been used to solve the problem. And I forgot to mention, but please feel free to stop me anywhere during my talk and ask questions. It's okay if I don't finish all the slides. I think it's important that we sort of are on the same page as we move along. Okay, so what is today's talk about? Well, I already told you probably that much ink has already been spilled on Gaussian linear regression with the lasso. So what am I talking about today? So first of all, what if I'm not willing to assume a Gaussian model in my data? What if I have non-normal data? To be very specific, say, you could say, well, instead of seeing a continuous response, maybe I'm seeing a binary response, or I'm seeing a count response. And for these sort of responses, probably assuming a Gaussian distribution is not quite appropriate. Second, coming to the predictors. So I'm still talking about selection, variable selection in the regression context. So I mentioned the response, but what about my predictors? Say again, I don't have continuous predictors. I do want to allow categorical predictors in my data. So how do I mean, there are ways to do variable selection for different types of data in regression, but how do I do selective inference? How do I conduct selective inference for the selected variables? Okay, now, are these data, do you see such data sets in regression? Yes, of course. These data sets with different data types are quite common in regression. And I'll just give you one example that I've been looking at, which is data from the National Health and Nutrition Examination Survey. It contains demographic, nutritional, and health-related data. The response here is incidence of depression. So you want to estimate the incidence of depression. So what you see is a binary response, which is whether the sample is a depressed person or not. And again, this is a data set where you don't just have continuous predictors, but you have a lot of categorical predictors such as race, health status, income, diet, etc. Okay, so forget about selective inference for now, but if I were to just select variables, what is the most natural regression to run for this data set? Well, I have a binary response. So when I have a binary response, we know that one of our favorite tools is the logistic regression. So I will look at a logistic loss function with the logit link function. And what about my predictors? Again, like I said, I don't just have continuous predictors, but I have a number of categorical predictors too. And when I have categorical predictors, it's common to encode categorical predictors as dummy variables, and they come naturally as groups of dummy variables, right? So a categorical predictor, which is say 3 levels, is usually encoded as 2 dummy variables, which come together as a single group. And the natural penalty here is not the lasso, but the group lasso, because when you want to select these groups of dummy variables, you want to select whole factors and not individual dummy variables. They make no sense. because you want to select the categorical predictor, or you don't want to select it in the model. So you want to select these groups of dummy variables together or not. But again, this is nothing special to do with categorical predictors. You could also think of continuous predictors, which are probably all related to the same characteristic. And the lasso is just a special case of the group lasso penalty. So when you have groups all of size 1, that's essentially the group lasso penalty coincides with the lasso penalty. So this is a more general class of estimation problems. And now I'm not interested in the quadratic loss function anymore. I want to deviate from it. And it could be a logistic loss function, but more generally in my paper, actually, you could look at a thrice differentiable loss function. That's all that you need. It doesn't have to be a loss function that's linked with the likelihood. But here I'm just giving you a more specific example. And the penalty that we look at is the group lasso penalty. All right, any questions? Okay, so now say I select my groups of variables. Let me call my groups of variables as GP. I unpack the variables in my selected groups, and the total selected variables from all groups is what I call, the set of those selected variables is what I call E. And that naturally gives me a data-dependent parameter that I want to infer for. Let me formalize it in the next slide. So once I select groups, I would model my Ys as independent Bernoulli random variables with this probability, where the probability that Yi takes the value 1 is now parameterized in terms of the selected variables, right? So I ran my variable selection algorithm, I selected variables, I used that to define a model on my data. And in this case, I'm doing a binary response, which is why I'm just showing you this parametric model. Now, the question is as simple, can we provide inference for beta E? But clearly, the set of parameters that I'm asking you to infer for are data dependent to set E. Okay, so before I move further, how about like naive inference? What if I use the same data to do inference? Probably a lot of people would know that that's not going to come with any guarantees of inference, but let's just do it and just convince ourselves that that's really the case. So I am varying the sparsity size, which is the number of groups in my data on the x-axis, and the y-axis is showing you the coverage rate. If the coverage rate is 0.9, then I would say that my method is valid. It's attaining the desired rate of coverage. Anything below that is invalid. And you can clearly see that as sparsity size is increasing, the effect of selection is waning away. So you see slightly better coverage probably as sparsity size increases, but nevertheless, all of them are below the nominal rate of 0.9. So that just says you can't reuse your data to do inference if you have used it to select the variables and pose a model on your data.
Is this the high-dimensional setting? Is P larger than n?
No. P is not larger than n. P is that's a very good question. P is 100 and n is 500. So P is not larger.
Why don't we do variables?
Very good question. So we do variable selection, even if for the regression test that I showed you. If you believe that not all variables make sense for your model, you might still do a variable selection. And even textbook examples for variable selection methods, it doesn't do variable selection. P need not be larger than. It's only when, of course, you need to believe that maybe some of these variables are just like, you measure them, but you don't know whether they're associated with Y or not. You could include them. Well, I think part of our task is also to get models that are simple to interpret. And what selection gives you is a simpler model. If you knew that the model that you define on your data need not be using all the variables, which are probably noise, then, and you could do with a simpler model, you might as well fit a simpler model to your data.
I think your question, so everything only is the starting point, some underlying true model with this many products. So the underlying model generate timeline to start.
There could be a true underlying model. So here, I mean, what after I select and I pose a model on it, that's a good question. It need not be the true model because selection isn't necessarily guaranteed to give me the true model. But it's only if you believe there is a true model. So selective inference, still like I didn't show you, didn't want to complicate matters for you. Selective inference, regardless of the quality of selection, gives you valid inference for a well-defined quantity. And that well-defined quantity is a mean of y that is best explained by the selected variables. But again, that's a general quantity and that doesn't have, but your true model, your selected model could still be a misspecified model to answer your question. But selective inference still guarantees you valid inference for a well-defined object.
So we're welcome to see that object.
Yes. Sure. What should I do?
Sorry, quick question. I'll ask it. So maybe relatedly, are these coverages that you're showing, is it for beta E or is it for the true beta?
No, it's not for the true beta, but it's for beta E.
So is that a fair comparison though?
Well, it would be even worse for the true beta E. If you wanted me to do it for the true beta, I could do it, but it would be even worse than this.
Yeah. Well, I mean, the issue is that sort of the naive approach is not designed to do inference for beta E, right?
Let me see if I get your question again. I didn't hear you.
The naive approach is not designed to give valid inference for beta E because it's not taking that selection step into account.
Yes.
Whereas
that's
selective inference,
exactly the point. Yes, that's exactly the point.
Selective inference naturally would give valid inference for beta E.
Yes.
But then if you compare the true beta, if there's a true model, which in this simulation there is, then it would be the opposite, that the naive approach, and in fact, under some assumptions, this actually is true, that the naive approach would give valid inference in some weird settings, whereas the selection inference, in order for it to give valid inference, would also have to have some weird assumptions holding for the true beta.
Well, I think you're saying, okay, so I think the assumptions that I can think of are screening. If you screen the support, then the target beta E coincides with the target that you're talking about, the true target, the true non-zero coordinates of the actual parameter, underlying parameter. But that's only in a world where you believe in a true model. I guess I belong to a school of thought where there is no true model ever. All you're doing is approximating models at different stages. And this is, where you are, after you selected variables, you posed a model, but even when you say I sort of believe in a model, it's probably, it might not have the problem of selective inference, but it's probably coming from somewhere and it's still an approximate model in all reality.
Sure. I mean, that's a fair point.
Thank you. All right. So what are the two challenges here for selective inference? Well, one challenge is selection with the group lasso has no easy description. And I'll show you in a bit. I'll explain both these points in a bit. And two, my data are no longer normal. So like I told you, a majority of work in selective inference for the variable selection problem has focused on normal data. So I'm specifically interested in asking the question, what if my data is no longer normal? But I'll try to address the first question, the first challenge in the beginning, and then maybe I don't have too much time to talk about the second point, but I'll try to make some quick points there. All right, so what am I going to do? I'm going to introduce something called randomization, and I'll do that in a specific form, and in fact, in a carefully chosen form to alleviate both challenges. And honestly, I do not know of any other way to alleviate both challenges without using randomization. And second, again, I won't get time to talk about this. This carefully chosen form not just alleviates both these challenges, that is, gives me a tractable form to the group lasso and allows me to do inference for non-normal data, but at the same time, it resembles data splitting during selection, in the sense that the way I would randomize would be asymptotically equivalent to doing model selection on a random split of your data. So if you have your favorite data split proportion, if you said, I'm willing to do data splitting on 90% of my data, meaning I'm going to use 90% of my data for model selection and leave a 10%, the remaining 10% for inference, then I could construct you an equivalent randomization, which would give you similar selection as data splitting on 90% of your data. Except for inference, I am not going to use just the remaining 10% of the data, but I have a way to reuse all my data for inference. So I am guaranteed to construct tighter confidence intervals and more powerful inference than data splitting. All right, so with that, let me move on to the actual method. So first part, I'll try to introduce randomization, and I'll try to tell you how we construct a selection adjusted likelihood. And I'll do all of this in a toy example. So everything would be, I've really tried hard to think like how to explain this method as simply as possible. And I thought it's best to do it in a toy example. But things are more complicated in reality, but the methods just translate. I just want to show you the key ideas through this toy example. So very simple example, N is 2, 2 samples, P is 2, 2 predictors. I have a group of size 2. So I have just one group of predictors, and I have 2 predictors. I group them as one group. And I run the group lasso. So you can see that's the group lasso objective. And X is just identity here. So made it really simple. The first part is a quadratic loss. So I'm just dealing with the first part of the challenge. So right now, I'm going to talk about just Gaussian data. And focus on the group lasso first. So how does the geometry, how does the selection event? So whenever you adopt a conditional approach for selective inference, you condition on the event that you selected the variables 1 and 2 in this problem. Now you have to describe that event. You need to be able to write out that event, because to work out a conditional distribution, you condition on an event. If you do not know how to work out that event, how to write down that event, you cannot proceed. Like you just theoretically know, well, you're doing conditional distribution, but you need to be able to simplify the conditional distribution, right? For that, you need to have a way of describing the conditioning event. So I condition on the event that E equals 1 and 2. I need to have a way of writing down that event. And in the case of group lasso, we can see that if I select variables 1 and 2, then this event is basically the set of all y such that the L2 norm of y is greater than or equal to 1. So it's the shaded region here. It's the complement of a unit ball, which is centered at the origin. That's how the selection event looks like. Well, you may say it's easy to describe. It is only in this toy example. Whenever I have multiple groups, not necessarily of size 2, I select some groups, I discard some groups. I do not have a clean way of writing down this event anymore. But this is just the toy example, which is why I know I can show you what the selection event looks like. Now, how is this different from the well-studied lasso, which has been the topic of discussion in a lot of previous work? So here I just want to contrast the geometry of the group lasso with the geometry of the selection events that you see in the lasso. So in the lasso now, say I don't have groups of variables. Instead, I have 2 groups of size 1 each. So I have a lasso penalty on my 2 predictors, on the effects of my 2 predictors. Now, if I select variables 1 and 2, how does the selection event look like? Well, it's a union of the 4 corners that you see here in this rectangle. And that's not surprising because what you must have, if you have ever seen papers in selective inference, the conditional approach works with the lasso because it used something called the polyhedral lemma, which means that the selection event with the lasso could be described as a union of polyhedrons or polytopes. And here, polytopes in 2 dimensions are nothing but rectangles. And you can see that the selection event is a union of 4 rectangles. And if you additionally condition on the signs of the variable, you no longer have a union of polytopes, but you land in exactly 1 polytope. But all in all, the point that I was trying to make is that the geometry of the selection event is very different if you move from the lasso to the group lasso. I see a hand again, please. Oh, it was from before? Okay.
Sorry, it was from before.
Sorry. All right. Now, how do I solve the problem? I told you that event that I see in the group class. It's actually very hard to describe. I mean, I could do it in my example, but in general, it's very hard to describe. So how do I hope to solve it via randomization? So what is randomization first? And how does it simplify the problem? Okay, so to introduce randomization, so instead of running the group lasso, I would be actually running a further version of the group lasso, or a randomized version of the group lasso. So this was the original group lasso objective that I showed you. And now you just have an additive term to the objective of the group lasso, which is linear in the randomization variable omega, which is a random variable, nice normal random variable centered at 0 with covariance equal to eta square identity. Yes, Daniela.
I mean, I understand maybe with the design being here, why would it be harder with one student? I feel like if your group is more than 10 students, then you have like a first year instead of a circle. And then if you have multiple groups, they're going to be close perfectly because they're going to identity design.
I think here it's easy to write because I just have one group of variables, either I select it or I don't select it. But when I have multiple groups where I can select only a subset, where I'm probably going to select a subset of them and not select others, it's a very ugly method.
You're defining your identity, so it could be composed of separate.
So you're saying in the case that the design matrix is an identity, does it get simpler with the group lasso? It will probably if you have an orthogonal design matrix.
Okay, but you're saying that if you had a figure in your equation, there's no design matrix. Yes. Then you had a design matrix.
Yeah, it would be complicated. But even for the standardized group lasso, the standardized group lasso doesn't have really an orthogonal design matrix, but the groups themselves are orthogonal. So I know that even for the standardized group lasso, it's just very ugly to that. It doesn't work out, but that's because it's not that you have an identity design on it, which is that the groups are right. All right. Okay, now I have this additional term, so I decided not to work with the original group lasso problem, but introduce randomization in it. And in this specific form, where I added a linear term in the randomization variable omega, linear term which is linear in omega as well as beta. And this randomization variable is perfectly Gaussian and variable centered at 0 with a covariance eta square identity. It may not be eta square identity, but for the toy example, I just made it simple. It could be any covariance. Now, how does the geometry of the selection event change? With randomization, nothing changes. It's really a shift of origin. So earlier I told you that the selection event that we select variables 1 and 2, the 2 variables that can be expressed as a complement of unit ball centered at 0. Now it's still the same geometry, except that it's now if you fix omega for a fixed omega, the slide that you're looking at is again the complement of a unit ball centered not at the origin, but at omega. So it's just a shift of origin from, it's just a shift of centering of the ball from origin to the randomization variable omega in the previous case. So you're like, okay, then why am I randomizing? The geometry isn't changing much. What am I accomplishing by randomization?
So here, omega is but you're saying that it's centered at something that's hard.
No. It's so this is just a fixed slice. I'm not showing you that here. So if I fix omega for a fixed omega, it's actually this region. It's the space in it's the space of in R4 actually y and omega such that y plus omega in L2 norm exceeds 1. That's the actual description, but how do I show you in picture? Something like if you fix omega, then it just means that I have simply taken the same unit ball, but not centered any longer at the origin, but centered at omega. And I'm just like visualizing the image. But you're right that this is actually a space in R4 because y is 2-dimensional and omega is 2-dimensional. Next question. So again, what did I really accomplish by randomization? Well, I told you that I use randomization to write down, to be described the selection event very simply as sign constraints. Now, how do I do that? That's because, say beta G is my group Lasso solution or the group Lasso estimator, then I know that if this solution satisfies this equation, and that just comes by taking derivatives of the objectives that you see right above. So that should be really what the group Lasso solution or estimator satisfies. I'm going to use this relationship to do a change of variables. So I'm going to quit trying to describe my selection event in the original space y and omega. And instead, I'm going to transform a space for a change of variables and try to re-describe my selection event, the same selection event, in new variables. And that's exactly what randomization allows me to do. So if you look at this form, so if you look at the previous equation, this is what my group Lasso estimator satisfies. And this is just drawing connection with selective inference that has been done with randomization beforehand. So you add noise, some additive noise to your response variable to selective inference. And essentially, if you try to look at this form, it's no different because it just means I'm doing selection on a further version of y, which is y plus omega, if I just rearrange the terms in the equation and take y to the side. And there has been this also cross connections with data training, which I think is word coming from Daniela's group, which does selective inference using further data or data training, as she calls it. You construct like two versions. You try to split your data and copy with the different version of data training. So you do selection on a randomized or perturbed version of y. So you can view it as just adding noise to your response y and doing selection on that as well. Okay, now what do I do with it? So far I just showed you, okay, this is how I randomize, but I've still not told you what do I accomplish with randomization. So this is that same map that I showed you, which is the equation that the group Lasso solution satisfies right here. Now, what I'm going to do is I'm going to write my group Lasso estimator slightly differently. So what I'm going to do is I'm going to write the group Lasso estimator in this form, where I decompose it into the L2 norm or its size and a unit vector. So I basically write it in the product form, where the L2 norm of the selected group is what I call gamma G. And The direction vector is what I call UG, which is the unit vector. Now, once I write my group lasso solution in this form, what I'll use is I can write omega as minus y plus wherever I see beta g, I'm going to write it as this product form gamma g times UG. And you can see that here I had the unit vector sitting here, which comes from the derivative of the group lasso penalty at the solution. That is just UG. So I can treat this pi as a change of variables, which takes my omega and which basically takes gamma g and UG as arguments and outputs omega. So I'm going to use this change of variables. And if it is like, I keep mentioning change of variables, but what it is essentially doing is now I'm like, okay, let me not try to describe my selection in terms of y and omega, but instead I'm going to express my selection event in terms of y and these new variables gamma g and UG. So I did a change of variables from omega to gamma g and UG. And what it does now is if you try to look at the selection event, you can write it as simply gamma g being greater than 0 and the N2 norm of UG being equal to 1. So UG is just a point on the unit sphere. And gamma g is just the size of the selected group, which obviously has to be greater than 0. Oh, little g is that single group that you selected, that single group of two predictors. So here in this toy example, you have just a single group with two predictors, 1 and 2. Either you select that group or you don't select that. So you will select the difference only if you select the best. So that G notation is for that one group of variables that is present. And like I said, the main thing that I'm trying to do is I've given up on trying to describe the selection event in terms of y and omega, but I could essentially write the same selection event in terms of y and gamma g and UG. And that removes constraints from y. I simply have constraints, separable constraints on gamma g and UG. And these constraints are fairly simple. Gamma g must be just greater than 0 and UG must lie on units. And this is true even when I have, like in general, not just one group, but multiple groups. And I could express the selection event similarly. Now, what are we going to do from now on is not work with just this selection event, but I'm additionally going to condition on UG. So I'm also going to condition on UG, which is a little bit of extra conditioning. But in the case of how to see how to draw connections with what has been done previously. So so one line of work for the lasso conditions on the signs of the selected variables along with the set of selected variables. So when the groups are just singleton with size 1, these UG just correspond to the sign of the selected variables. So here I'm also going to do the same. I'm going to condition on UGs. And once I condition on UGs, I remove this constraint because I can just treat them as constant, and it just leaves me with sign constraints of this form. So I have just as many sign constraints as the number of that I select, and it just needs the size of the L2 norms of the selected groups to be greater than 0. Those are just the support constraints. Okay, so that was with the selection event. Now let me try to write down the likelihood of y conditioned on the fact that I selected a group of two variables, 1 and 2. And also, like I said, I'm conditioning on UG. I'm conditioning on the values of the unit direction vectors. Now, how do I get this conditional likelihood? So we'll start with the unconditional likelihood. And again, I'll start with the variables that were there in my selection. So I had y, but I had some additional noise variable omega, right? And both of them were nicely Gaussian here. So I just have their unadjusted or unconditional Gaussian likelihood. And I forgot to mention, actually, randomization is not just Gaussian, but it is independent of y. So the unadjusted or unconditional density of y and omega is just a product of the marginal densities. Okay, Now, I described my selection event not in Y and omega, but in terms of Y in these new variables, gamma, G's, and U's. So ultimately, if I describe the selection event using gamma, G's, and U's, if I don't know the probabilistic distribution of these variables, it's useless. You know, I solved maybe part of the problem having a simpler description of the selection event. But if I just don't know the probabilistic distribution of these variables, I mean, what do I do with this simple description? It's just useless. But you know, that's again why I keep mentioning it. That's where the change of variables helps me. I know the distribution of omega. I knew how I obtained these new variables. These new variables were obtained from omega using a very specific change of variables. So I should be able to like use the change of variables to know the probability distribution of the new variables. That's all that I'm doing here. I'm trying to find the unconditional distribution of my new variables, and because I had the change of variables phi right here defined to phi, I replaced omega with phi, and I have a Jacobian because of the change of variables. So every change of variables comes with a Jacobian, and that's the Jacobian term, which is not a bad term. I know what this Jacobian is here. Yes. Oh, so Y is normal, is a normal random. That's very good question. I should have mentioned it. Y is normal, centered at beta, and with covariance identity. So for now, I'm just working with normal data, and I have a normal model for Y. That is just the unadjusted likelihood for Y. And when I write P, this is just the Gaussian density evaluated at Y, centered at beta with covariance. Very good. I should have done. So if I look at the unconditional likelihood of Y and omega, it's just the unconditional Gaussian density for Y. This is the unconditional density of randomization. And now I'm like, okay, next step, I'll write the unconditional density of my new variables, which is Y, gamma G, and UG. And that I obtained by just using the change of variables, because I know that gamma G and UG are related to omega through this map path. So I just do a change of variables to write the unconditional density of Y, gamma G, and UG, which gives me this. But again, I'm interested in the conditional likelihood because that is the real selection adjusted likelihood, which adjusts for the effect of selection. So this is the Jacobian term comes from the change of variables. So this is another term because I did a change of variables. There is a Jacobian, and the Jacobian is 1 plus gamma G here. And the selection adjusted likelihood now, because of what I conditioned on the fact that it's selected variables 1 and 2, the group with 1 and 2 variables. And I condition on mu G, so I take this constant. So what I'm left with is the single sign constraint on gamma. So the transitive density or the conditional density that you get here, or the conditional likelihood or the selected adjusted likelihood is very simple, because the region to which you're truncating happens to be a very simple sign constraint. And it's so example, it's just a single sign constraint, which just constrains your gamma G to the positive half. And for more complicated problems, it doesn't get more complicated. The sign constraints on the sizes of on the N2 norms, the selected groups are again just sign constraints. So you just have as many sign constraints as the number of n selected. So it doesn't get more complicated than this. Okay. Now, that's what the selection adjusted likelihood is proportional to. If I really have to give you an expression of the selection adjusted likelihood, I need to have the normalizing constant. And this is what the normalizing constant, which integrates over Y and X. So the display on the previous likelihood was what it's proportional to. I took the unconditional likelihood, truncated it to a region, and now I'm writing that same likelihood with the normalizing constant. All right, I am running short of time, so I should be a little quicker. So what does the selection adjusted likelihood now look like? So this is that normalizing. So this is the usual, this is the part that you get from the usual Gaussian likelihood of Y. But what happened when you adjusted for selection, you have an additional correction term in the likelihood, which is the log normalizing constant or the log probability of selection. And again, in reality, this log probability of selection of the log normalizing constant is an integral that we don't want to compute. In the toy example, it's easy to compute, but now in general, it might not be that easy to compute. So what we do is to avoid this integral, we replace the integral by the mode of the integral, which is also called Laplace transform. All right. So this gives us a tractable selection adjusted likelihood at the end of the day to work with. Now, I haven't even gotten to the method. So I told you how we construct a selection adjusted likelihood with randomization. But what do I do with the selection adjusted likelihood? Okay, I have a tractable likelihood that I can write on paper, but how do I do inference with that likelihood? What you would do is, so this is again an approach which is fairly different from a majority of the selective inference work that I've seen. It directly works the likelihood, it computes its maximizer, the selective MLE. So you compute the MLE, there is a nice estimating equation for it. And you also compute the Hessian matrix of the log normalizing constant, and that gives you the observed difference. So once you have a nice likelihood, you just compute the maximum likelihood estimator and the observed Fisher information matrix. And then we just do the intervals that we construct are very much like our standard inference. They're centered around the MLE. So now, unlike a lot of the other selective inference papers where you see asymmetric confidence intervals, these are not asymmetric confidence intervals. They come with a natural point estimator, which is the maximum likelihood of the selection adjusted likelihood. They're centered around the MLE, and they're scaled by the inverse, by the entries of the inverse Fisher information matrix. Because you know that the MLE is usually, like classical theory, this tells you MLE is asymptotically normal, centered around the two parameter, and scaled by the inverse of the Fisher information. So that's what we do. Except the fact that now we compute both these four ingredients, the MLE as well as the Fisher information, from an adjusted or selection adjusted likelihood instead of the usual likelihood. Does it work? Well, this is a picture in the bivariate example, which just tells, yes, selective inference via maximum likelihood does work. And this method relies on 2 bits of information. So you need to be able to compute the maximum likelihood estimator as well as the Fisher information matrix. And this is basically the last piece of the puzzle, where I'm telling you what exactly. So at some point we use, instead of the actual normalizing constant, we use a Laplace approximation for the normalizing constant. Now, what does computation, what does it require us to do? Well, computation, all we have to do selective inference now is solve a simple optimization problem. And it is an optimization problem with a relatively simple objective, and it's in fairly low dimension. So for the toy example, it's just a one-dimensional optimization problem that we solve. Now, I'm going to skip over this, but essentially this was telling you where does this optimization problem really come from? There is some convex analysis. So we write down the MLE problem, and when we write it down, we can see that the optimization problem involves a function delta star, which we can recognize as convex conjugate of a function. And if we try to attempt to write the dual of this problem, that essentially gives us this optimization problem. So long story short, all we have to do is solve this optimization problem, and that gives us the MLE as well as the Fisher information, both ingredients that we need to construct our intervals. Now, for a large part of the talk, like I told you, I just showed you randomization to redescribe the selection event, get tractable selection adjusted likelihood, and do inference via maximum likelihood for normal data. But part of this challenge was, we wanted to go beyond normal models and do it for non-normal data as well. And in the paper we do. So back to our logistic problem, how do we go beyond normal data? Well, I just want to quickly say, I don't want to show any theory here, but you don't have normal data, but when you compute a refitted estimator, so say you selected a group of variables, 1 and 2 in this toy example, then you could always refit your data to the reduced. In this case, it's not really reducing any data, but say you had general data, you selected certain groups, you selected variables E, then you could refit your regression to the reduced data with just those selected variables or selected predictors. And that would give you a refitted estimator. What you can show in general is that this M estimator is it is asymptotically Gaussian. So even if you don't have exactly Gaussian data, you have, like, say, you work with logistic regression or Poisson regression, but this refitted estimator or this M estimator in your reduced data is asymptotically Gaussian, centered around at this parameter beta E that you're trying to perform with covariance, with some covariance sigma. And the tool that helps you apply this Laplace approximation post the failure variables is something called contraction principle in large deviation theory. So again, I'm rushing through the slide, but what it means is that if you have variables which are asymptotically Gaussian, a probabilistic justification for the Laplace approximation, it seems like a numerical technique, but the probabilistic justification of it comes from large deviation prediction. So if these variables, if your original variables satisfy a large deviation limit, then after you do this change of variables, which was facilitated by randomization, you can still justify the Laplace approximation using something called a contraction principle in large deviation limits. And I'm not going to go over further details, and rather I want to end by showing you some empirical results. So here we have 3 non-zero groups of continuous predictors, and we also have categorical predictors. So we have a mix of continuous and categorical predictors, and we vary the number of non-zero categorical predictors between 2, 5, and 7. The dimension of the problem n is 500 and p is 200 here. And covariance of randomization has been carefully chosen in a way. So I don't just have normal randomization, but I actually choose the covariance matrix of randomization in a special way, such that selection mimics data splitting. So here is a plot for logistic regression, where on the first panel you see F1 score. So we can just look at the MLE is our method, which is in green. Blue is data splitting. And the point here is you're computing F1 scores after selection just to see if the quality of model selected by data splitting and this new randomized class looks similar or not. And the point that I'm trying to make is that they're not just asymptotically equivalent in theory, but in practice, it seems that they're producing, because look at the medians of the box, they're roughly similar. So conditional on our method as well as data splitting, choosing the same model, we just want to see how they do in terms of capability. Do they guarantee validation? Yes. So you can see that data splitting is a little below 0.9 in this example, but because we maybe don't expect it to be exactly around 0.9. And ours is a little above 0.9. But you can see that we get valid coverage, we reach the nominal level, and we construct shorter intervals than data splitting. So even if we produce the same quality of models as data splitting, we produce shorter intervals and data splitting. And the story holds up for Poisson regression. And again, Poisson on logistic are 2 examples where you did have normal data, but there is nothing special about these likelihood estimation problems. In fact, in the paper, we show that you can do you can use the same techniques for more general estimation problems, such as say quasi-Poisson, which doesn't, where the loss is not associated with any likelihood. So today's talk, I hope that I showed you randomization in a certain form, which allowed us a nice change of variables. And I don't think this idea of randomizing it in this form is specific to the group lasso. In fact, I have previously done it for another problem where you have a non-convex objective. It's not even as nice as the group lasso, which is a perfectly convex selection algorithm that you solve. I've done it for sparse multitask regression with a penalty that just looks non-convex. But I hope that this form of randomization can be also used in other problems, in other non-polyhedral selection problems, where the selection event is not as nice as the lasso and can be written as a union of polyhedrons. But you can do this change of variables to instead like describe the selection event in new variables, which are actually optimization variables. And it can be directly expressed in terms of those optimization variables. Two, even though the example that I showed you was logistic regression, but in reality, we are actually doing distribution-free selective inference with no parametric assumptions whatsoever. And third, again, this is something that I didn't get so much time to talk about, but once the paper drops, I hope this connection is made clear. There is a direct asymptotic connection of this form of randomization with the more familiar data splitting. Except that this form of randomization now allows you to reuse all the data instead of being wasteful as data splitting. So some of the two papers that I talked about today are approximate selective inference via maximum likelihood and approximate post-selective inference for regression with the group lasso. But both these papers are strictly for Gaussian data. But the new paper, which allows you to do more general estimation problems as well as distribution-free selective inference, is going to drop soon. And thank you. And if you have any questions, please let me know.
Any questions? Maybe naive, but you said omega is random. So, and then you seem to characterize it with this other variable, gamma G, and the other one. So where is the randomness coming from, being generated from? Is it omega random, and then you select this variable in such a way that reflects omega, or the other way around? Those are.
So am I considering the randomness in omega is a question?
Yeah, but where it comes from here? I mean, there's this mapping. Is that deterministic?
The mapping is deterministic. The mapping is deterministic. It's a mapping from one random variable to another random variable. But the change variables is
omega is random, and which one of the two? The mapping is gamma G and UG.
Gamma G and UG are random variables. So omega is a random variable whose distribution I know because I do omega from a normal distribution. It's a very normal looking random variable whose distribution I perfectly know. But then this mapping allowed me to relate it to these optimization variables, gamma G and UG, which come from the group lasso estimator after I solved the selection algorithm. But this mapping just helped me specify the distribution of these new variables. Without this relationship, of course, I wouldn't know what the distribution of the optimization variables is.
How is it special that you use omega to follow or?
Yes, very good question. You could have done something else. So in the case